All right, let's dive right in. Today, we're talking about something that's totally critical to how fast your apps feel, but you almost never see it. We're going to pull back the curtain on the secret life of a database index. It's this hidden engine that makes everything feel snappy, but it's also got a dark side that can slow things down to a crawl. So, have you ever noticed this? A brand new app feels lightning fast, right? But give it a few weeks, a few months, and it just starts to feel sluggish. It's a classic problem, and it drives developers crazy. And you know what? The culprit is usually hiding in plain sight. It's the very thing that was supposed to make it fast in the first place, the index.
Okay, to really get this, I want you to picture a library, like a brand new, perfectly organized library. Every book is exactly where it should be. Finding what you need is a piece of cake. But now, imagine what happens over time. New books get shoved in, old ones are taken out, and things start to get messy, right? Gaps on shelves, disorganized sections. That perfect card catalog now points to a total mess. Well, believe it or not, that's almost exactly what's happening inside your database index.
So that brings us to the big problem, right? How do we keep this digital library of ours tidy? It really all comes down to managing the one data structure that powers pretty much every database index out there.
And that structure is the B tree. Seriously, it's an absolutely brilliant piece of engineering. Its whole job is to keep data sorted so you can do super fast lookups. You can think of it as this magical self-organizing card catalog. But here's the catch. Even something this clever can't escape the messiness of the real world.
So where's all this mess coming from? Well, it turns out there are four main culprits, things that happen all the time in a normal database. You've got these expensive page splits that just create clutter. Then there are sequential inserts that cause these huge bottlenecks, total traffic jams. Plus, building new indexes can be super inefficient. And finally, you have ghost data from deleted records just wasting space. But don't worry, for each of these problems, engineers have come up with some really clever solutions, and we're going to break down every single one.
All right, first up, rebalancing. Let's talk about those really expensive page splits and a much smarter way to shuffle data around.
Okay, so here's the deal. When a page of data in our B tree gets completely full, the default move is to just split it. It creates two new pages, both only half full. Now this sounds simple, but it's actually really slow. You're writing new stuff to the disk, you're updating all the pointers, it's a whole thing. And if you do this over and over, you end up with tons of wasted space. It's just like having dozens of half-empty bookshelves cluttering up that library we talked about.
This is where rebalancing comes in, and it's such a smart solution. Instead of just splitting the page right away, the system takes a peek at its next-door neighbor, and if that sibling page has some free space, bam, it just shifts a few elements over. It's that simple. It's this one tiny, intelligent check that completely avoids a way more expensive operation. It keeps our pages way fuller and our whole index nice and compact. So much better.
Okay, let's move on to the next big bottleneck, optimizing appends. This is all about what happens when you get a traffic jam from inserting data in a nice, neat order and how we can create a special fast lane to deal with it.
Man, this next one is a classic database headache. I'm talking about when you use things like auto-incrementing IDs or timestamps for your index key. Think about it. Every single new record is trying to get added to the exact same spot, the very end of the line. It literally creates a Congo line of data, all trying to write to the same page. This creates a massive bottleneck, what we call a hotspot, and it forces that one poor page at the end to just split and split and split.
And the solution for this is just beautifully simple. It's called write-only appends. Basically, the database gets smart, it sees this conga line pattern forming, and pretty much says, you know what? Forget the normal rules. It completely bypasses all the complex logic of trying to find the right spot in the tree and just tacks the new data straight onto the end. It's like a purpose-built express lane, and it makes this super common task way, way faster.
Okay, so we've got a handle on adding records one by one. But what if you need to index like 1 billion records all at once? The one-at-a-time thing just isn't going to cut it. For a job that big, you need something industrial strength. You need bulk loading.
Seriously, if you try to build an index for a massive table by just inserting row after row after row, you are going to have a very, very bad time. It's not just that it's painfully slow. The B tree you end up with will be an absolute disaster, just a mass of half-full pages and tons of fragmentation. It's basically the worst-case scenario we saw with all those page splits, but on a massive scale.
And I mean, the difference here is just night and day. Bulk loading is a completely different approach. You take your data, sort it first, and then build the B tree from the bottom up. There are no splits, none. It is incredibly fast, and what you get at the end is a perfectly packed, super efficient index. We're talking nearly 100% page occupancy. That just means every page is as full as it can be. Compare that to the 50 to 75% you get with the standard way. No contest. This is how the pros build a tidy index from the get-go.
All right, we've talked a lot about adding data, but what happens when you remove it? That brings us to our final big challenge, taking out the trash. Yep, it's time for garbage day.
So there's this great quote from the book Database Internals that really gets to the heart of the problem. It says, since deletes only discard cell offsets and do not relocate remaining cells, freed bytes might end up scattered across the page. Basically, what that means is, for performance, when you delete something, the database doesn't actually clean up the mess. It just erases the pointer to the data. It marks that spot as empty, but the old data is still there, taking up space. And over time, your data pages get riddled with these little holes of wasted space.
And this image shows you exactly what that looks like. You've got your live, useful data sitting right next to what is essentially garbage, data that's been deleted but is still physically there. That is fragmentation, plain and simple. And it's bad news, because it means your database is way bigger than it needs to be, and it's slower too, because your disk has to read past all that useless junk to find the stuff you actually want.
So how do we fix this? Well, with a process that's usually called garbage collection or, in some systems, vacuuming. You can think of it like a dedicated cleanup crew that just runs in the background. Its job is to go through all the data pages, find that dead data, clear it out, and then shuffle all the good live data together nice and tight. It reclaims all that wasted space and keeps the whole system lean and mean.
Okay, so let's recap the whole thing. We've seen how for every single one of these common problems that make our indexes messy and slow, there's a really clever solution working behind the scenes. Those costly splits, solved by smart rebalancing. The traffic jams from sequential inserts, bypassed with write-only appends. Building a huge index from scratch, supercharged by bulk loading. And all that wasted space from deletes, cleaned up by garbage collection. These four things, they are the real unsung heroes of database performance.
And that really leaves us with one big idea. Performance isn't some feature you just build once and then, check off a list. It's a constant battle. It's a fight against entropy, that natural tendency for everything nice and orderly to just fall apart and get messy. So the next time you're using an app and it just feels magically fast, take a second. Think about all these invisible, super clever optimizations that are working their tails off in the background